equation, I want to do this problem. Reason why I want to do this problem is because this is a very similar problem that you guys will be seeing in your lab practical. So I'm going to set it up for you, but you guys all know how to solve this. The only thing that's difficult might be balancing the redox equation. So let me go ahead and do this. Okay, we have titration. And when you do a redox titration, generally you're using a chemical in which electrons are going to be transferred. And the titrant's generally an oxidant or reductant, depending on what chemical you're analyzing. In this particular case, it's going to be potassium permanganate. The permanganate is the key chemical that's going to be taking the iron +2 to iron +3. So the question here is that the oxidation of iron +3 of 1.25 grams of iron ore. Iron ore simply means that it's contaminated. It's not pure iron 3. It's got some other impurities in there. Okay, but when it reacts with permanganate, only the iron 3 will react. So you have 45.3 mils of 0.0180 molar potassium permanganate. How pure is the iron ore? So the first thing that you need to do is you need to balance this equation. And the way you balance this equation is you always break it up into half reaction. Iron 2 goes to iron 3. And then, of course, we need an electron here. That's balance. We take the manganate, permanganate, and we know that it goes to manganese +2. We need to balance that. If you read the process of balance equation, we first balance non-hydrogen and oxygen elements first. Non-hydrogen and oxygen is manganese. The manganese are balanced. There's one in both sides. Then the next step is to balance the oxygen by water. I've got 4 oxygens here. I need 4 oxygens in the right side. I need 4 waters on the right side. Why do we balance it with water? Because the medium that you guys are going to be doing this reaction is aqueous. So water will be in there. The next step is to balance the hydrogen with positive cations. So I have 8 hydrogens here. I need 8 hydrogens here. Now my oxygens, 4 in each side, and my hydrogens are balanced. The last step is to balance the charge. I've got 8. I got a positive 8 in this, positive 7 in this side. I got a positive 2 in this side. Okay. The only way I can balance charges with electrons. Okay. So I can always bring the charge down. I can never raise it because electrons are negatively charged. So I need to bring 5 electrons here. 5 electrons and positive 7 gives this a positive 2 in this side. So I'm going to put 5 electrons here. Once I do that, everything should be balanced. I've got 8 hydrogens in both sides. I've got 4 oxygens in both sides. I got 1 manganese in both sides. This side is positive 2. The positive 8 and the negative 7. Sorry. Let's see. 7, 8 minus 6. The positive 8 and the negative 6. There's a negative 6 here. Makes that a positive 2. The positive 2 are okay for both sides. So that's our balance equation. The only thing I need in this balance equation is the number of electrons. This is 5. So I need to multiply that by 5. There are 5 electrons exchanged. Okay. I don't even have to complete that whole equation. Now I know the stoichiometric ratio. And the reason why I need to know the stoichiometric ratio is because now I can do this, the stoichiometry. This is the stoichiometry. It tells me that I need 0.10180 moles per liter of potassium permanganate, MnO4. The potassium is the spectator. And I need 45.04530 liters of the potassium permanganate. Notice the liters cancel. And then from the balance equation, I know that for every 1 mole of MnO4 minus, I need to react it with 5 moles of iron. How do I know that? I know that this is 1 and I know that that's 5 for the electrons to cancel. Okay, so, and then I'm going to erase this down here. I know that iron has a molar mass of 55 point, let me just double check, 55.87, I believe. So iron has a atomic weight of 55.85, pretty close. So for every 1 mole of iron, and that's +2. Remember, the molar mass of an iron +2 is equal to the molar mass of iron +3 is equal to the molar mass of iron, or the atomic mass, 55.85 grams. So that'll be the amount of iron that reacted with the potassium permanganate. When I get this mass right here, I'm going to take this mass and divide by the mass of the ore and multiply that by 100. Now I know the purity of that iron ore. And so this is what it looks like. I'm going to erase this. Okay, and I'll show you that right there. The balance equation is that. That's that. Take this, and we see that it's 0.2275 grams that actually react with the potassium permanganate. You guys know how to do this. This is chemistry 200. The only difference is that you needed to balance a redox equation. 0.2275 divided by 1.225 grams times 100, it's only 18.6% pure iron. Okay, so this is where we incorporate stoichiometry in balancing redox equations. Okay, make sure, and for those of you in lab, we will go over this. For those of you not in my lab, check out the Zoom video. The balancing process is not difficult to do, it's just very tedious. And the most difficult part of balancing redox equations is starting. I will point this out in the Zoom video. I will also point this out in my lab discussion today. But